Hey everybody, welcome back to my channel. Today we have the first of a two-part series, maybe three parts, but probably two, of using the dipole correction in quantum espresso. And this is going to be with application to calculating the adsorption energy of an add atom or an add molecule on a surface. The case we're going to study in this series is the adsorption of an add atom on a gold 111 surface. The reason why we're using the gold 111 surface is because we've used it extensively in past videos, and so if you're following along in the video series, you might already have the structure cut, and so it makes sense to make use of what we've already done. So I actually have had, when I was first learning this, had a lot of trouble conceptualizing what was going on in quantum espresso with regard to applying the electric field and how the dipole correcting works and why it's even needed. So before I get into cutting the crystal structure and using it in quantum espresso and plotting and interpreting the results that we get from quantum espresso, what I'm going to do is give a brief lesson on what exactly is happening. In quantum espresso, we have, when we apply the dipole correction, there are three main parameters we have to add. There's about 7 or 8 parameters we add in total, but these are the three that trip people up the most, so I'm just going to talk about them. So the three parameters are the Emax pos, or Emax position, this EO-preg. Can't exactly figure out what this O-preg is, but I'm sure somebody out there will let me know. And the electric field, which is applied as a sawtooth potential, which you'll see why it's called a sawtooth potential in a second, also uses Emax pos plus EO-preg minus 1. And I'll show you why this sort of, where this term comes into play. Okay, so why do we need dipole corrections when we want to calculate the adsorption of an add atom on a surface? And it's because, let's say we cut a surface and then we add an atom. Well, now basically we have a dipole that has been created in our structure, and this affects the potential energy of the vacuum. And basically, long story short, is when we do these computational studies, we want to make sure our potential is as quantitatively accurate as possible and as realistic as possible. And when you have the vacuum, you should have a flat potential energy surface or something near flat. And when you introduce these add atoms into quantum espresso, what happens is that the potential in the vacuum is no longer flat. And when the potential in the vacuum is no longer flat, then you have effectively a sawtooth potential that was induced by introduction of the add atom. So let me just show you what's going on first and how it's going to be applied in quantum espresso. So let's say we have our structure. So this black box here, let's say this is our unit cell that we put into quantum espresso. And therefore these repetitions below and above the middle box are going to be the periodic images of our unit cell in quantum espresso in the C or Z dimension. And so what I'm going to do is just sort of draw our gold heterostructure on here. So like we're going to end up making gold slab that sort of looks like this. Okay, and there's of course a lot of other atoms in there, but our gold surface is basically going to look like this. It's going to be a bunch of gold atoms in here. Okay, you basically get the picture. Okay, and this of course is in periodic in the A and B or X and Y dimensions. And so what happens is when you put an add atom on the surface, let's say we're going to put a fluorine atom here, the potential in the vacuum will end up becoming slanted, so to speak. It won't be flat. And what this is it mimics the effects of the sawtooth potential that is used to replicate the potential that would be how the potential would change under the influence of an electric field. And of course, we are not using an electric field, but yet we get these effects, and it's not ideal. And so we correct the we correct the perturbations, so to speak, to the potential that are caused by the introduction of this add atom through a dipole correction to sort of cancel it out. And when we apply the dipole, if you just read the documentation in Quantum Espresso, they give you these three parameters to use with the electric field application, and it's not always straightforward how they're applied in this situation. So what happens is the electric field begins from Emax position plus EO preg minus 1. So it begins from minus, in our case, if you use these two values, it begins from minus 0.05. And it increases until it hits Emax position. So it's going to increase like this until it hits Emax position. Okay, then it's going to decrease until EO preg plus Emax position. So it's going to decrease until 0.95. So here, when we're at Emax position, we're at 0.9. So now it's going to decrease basically until here, because this is the periodic replication of 0.95, right? So now if we were to move into this top cell, 0.95 of the bottom cell is minus 0.05 with respect to this top cell. So this minus 0.05 is effectively going to be the same thing as if I were to put this here. Like this. If I were to go like this. Okay, let me just delete this. Oops. Okay. That's just a little arts and crafts while we wait. Okay, so we have this. So if I were to move this right here, you could see that this 9.5 position is sort of like right here, right under 1. And so what happens is now I will decrease from Emax position to Emax position plus EO preg, which is like this here. And then what happens is I'm going to then re-increase to Emax position, which would be like up here. Okay, this would be a linear increase. And then I will decrease again. And likewise down here, we would be slightly decreasing to Emax position, which would then go down like this. And you can see here, these red lines I drew, these are your sawtooth potentials. And what you want to do is you want to make sure that your heterostructure, your surface and add atom, are inside the region where the slope of the electric field, which is the red line, doesn't change. So you can see that the slope of the electric field is changing here, it's changing here, and it's changing here. And what you want to do is make sure that the charge density of your system, which I'll put just sort of around like this, is not interacting with the change of slope of this potential of the sawtooth potential I have in red. And so this is basically what's going to happen. And what we need to do now is construct this gold structure here. We're going to do a calculation on it using, we're basically going to calculate the electrostatic potential. I'm going to show you that the potential is flat in the vacuum regions. And then what we're going to do is we're going to add a fluorine add atom onto the surface, and I'm going to show you how the energy is no longer, the electrostatic potential is no longer flat in the vacuum region. And in the next video, we're going to apply the dipole correction. Okay, so without further ado, let's go make our structure. So let's go to Vesta. Let's open the 1-on-1 unit cell we have from past videos. Okay. So what I'm quickly going to do now is add vacuum to this structure. So I'll do that by cutting off the periodicity in the A and B dimension. I'm going fast here because this is an advanced video in the series, and you should have a firm grasp on how to do these processes by now. So we're going to export data. We're going to just call it XYZ. We're going to save. Don't save the hidden atoms. We're going to come here, get our unit cell coordinates, go back to the VASP. Again, the reason why I'm doing this fast is because you should have a firm grasp on how to do this now. And then we're going to make the vacuum be 30 angstroms, just for a nice healthy vacuum. Okay, save. Open this up in Vesta. And you can see here, wow, that's a lot of vacuum. And so what we're going to do is increase the position of every atom in the unit cell to the middle of the vacuum. So let's go back here into our VASP. And right now, the middle of our unit cell, we want to be at 15. So let's take our middle atom. Actually, we have, let's see, we want the middle of this unit cell to be at 15. So what we have to do is calculate halfway between this distance and then add it by 15. So what we need to do is take this number, divide it by 2, okay, and then do this plus 15 is 18, and then take each one of these subtract these numbers from 18. So let's open up an Excel spreadsheet. Okay, and then we have, I'm going to take these numbers now, copy them here. I'll just take this number here. This will be equal this minus this. Oops, other way around. This minus this. Okay, take these coordinates, go back into here. Just going to paste them quickly so I can then copy them as such. Paste them into here. Pretty tedious process. Save, and let's reopen our structure. Okay, so now we have our gold unit cell such that the center is at 15 angstroms. So now what we're ready to do is, if you can now think about how this relates to what I have drawn here, you can see that in absolute coordinates, 0, this 0 over here corresponds to this 0 in my unit cell, and this 1 would correspond to here. So you can almost vision the electric potential being applied here. But first, we're not going to apply the electric potential. We're just going to calculate the bare electrostatic potential, and I'm going to show you that it's going to be flat in the vacuum region. Then we're going to add a fluorine atom, and I'll show you how it becomes perturbed, so to speak. So now we are going to open up Quantum Espresso. Here I have an input file already made, ready to show you guys. So there are many things wrong with this input file in terms of it being the best input file, but it is a functioning input file for illustrative purposes. What I mean by things being wrong is that, for example, this E-cut wave function and E-cut rho are not necessarily the most optimal ones for this gold structure. In order to get the most optimal ones, you need to do a convergence study with respect to this parameter. Same thing with this Gaussian smearing. It might not be the most optimal one for this structure. Definitely, you're going to want to use a way tighter K-point mesh. For a structure like this, I'd probably recommend a 12 by 12 by 1 K-point mesh. But again, this is something you need to figure out from performing convergence studies. So what I'm going to do now is upload the atomic coordinates that I have here into Quantum Espresso. So I'll need to re-add the atomic labels. Okay. Let me get the unit cell parameters. I am going to add a mixing mode here. as, because we do have a lot of vacuum, I'm going to add the local TF mixing mode. Okay, so what I'm going to do now is I'm going to run test to see if this quantum espresso file runs. So I'll do that by pw.x xscf.in. Okay, looks like, oh, species U in atomic positions is non-existent. Oh, that's from pasting, should be AU. Okay, let me remove the crash. Okay, so it is running, so now I'm just going to submit the job. It only takes a few seconds. And where I got this procedure from to be able to plot and average the electrostatic potentials is from a very nice blog I read online. I will provide the link to that blog in the description. The person, I think, did a very excellent job showing how to do these calculations and providing input files you could use. So mine are largely based off of the work he did. Also, I think the same person asked various questions in Quantum Espresso forums, and so I'd like to just thank him for a minute. I don't have his name off the top of my head, but I will provide a link in the description of the video. Okay, so the calculation is done. I'm just going to now run this x.plot.in. I'll just show you what this looks like quick. It's just very simple. So what I'm going to do now is I'm going to make a temporary directory, and I'm going to run the plot file. So x.plot.in, x.plot.out. Just so you know, these things ending in .x are the Quantum Espresso executables, and they act on the things that start with x. You don't need to have these x's here in the beginning. For example, I could have pp.x acting on plot in, but I like to have the x in front of the programs and the .x, of course, at the end of the executables, sort of acting on the programs. So I'm going to run this. Okay, that just takes a second. And now I'm going to run the average.x. So vi.x.average.in, just to show you what this looks like. It's another very simple script that I got from the wonderful reference. And now I'm going to do average, if I can spell it, average.x, x.average.in, x.average.out. Run it, it's done. Okay, now I'm going to move this over and we are going to plot it. Oh my god, it keeps doing this weird thing. Okay, here we go. So now we have in my projects, YouTube, Quantum Espresso. Okay, so what we are going to do now is we are going to move over the average data, which I have here. And I'm now going to this plot.plt, which is a new plot script I have. And we are going to plot the data, and the data looks like this. The first column is going to be the atomic coordinates, and they are, as you remember, we had 30 angstroms in the C dimension. Here there's 56.67. That's because these are in Bohr units. So in my plotting script, I convert from Bohr to angstrom by dividing by the conversion factor between the two. So I'm going to now plot this. Okay, so it looks like our potential goes below 0 a little bit here, so I'm going to extend the y range to -1. Okay, that doesn't look as clean, so I'll just up the bounds. Okay, so here is our electrostatic potential for our gold atom. And you can see we have basically 4 atoms in the Z dimension. Well, like 1, 2, 3, 4. So it makes sense that we see this sort of pattern here. And now what we're going to do is we're going to add our fluorine atom into the Quantum Espresso file. So I'm just going to go into this VAST file. I'm going to add a fluorine atom, just one. And I want to put it at the center of the unit cell, so I'll find coordinates that correspond to the center in the X and Y dimension. And in the C dimension, I'm going to just add two angstroms of vacuum. So 18.5 will then become 20.5. Save it. Let's open it in Vesta to see how it looks. Okay, here's our fluorine atom. Go to space filling model. You can see it there on the surface. Now let's see how the introduction of this fluorine atom affects the electrostatic potential we have previously. So here I have the unit for my fluorine. I know I'm moving fast in this video, but I want to make sure we cover everything and you can easily just watch this a few times. So let's go ahead and delete our old data. X.average.out, x.plot.out, x.scf.out. Okay. Now let's remove the submit file. I'm just going to check in temp, nothing is there. Okay, let's go into our self-consistent field calculation file. Now the number of atoms is going to go from 8 to 9. We're going to have a second type because we added fluorine. Now let's add in our fluorine here. Now I do have to get the pseudopotential for fluorine. I think fluorine is about 19 atomic units. So bear with me 1 second while I get the pseudopotential for fluorine. Okay, let's get the projector augmented wave 1. Okay, so now what we're going to do is run this calculation again, but now we have the fluorine. And just to re-stress, you obviously will want to do this at a relaxed geometry, at very tight K-point mesh, using optimal E-cut and E-cut row parameters and an optimal smearing parameter. I'm just showing you procedurally how to do such calculations, but in terms of using optimal geometries for your nuclear coordinates and optimal electronic structure parameters, you still have to do these things. Okay, that process of figuring those things out is actually a very trivial process, but it takes some time. It would take about a day usually. So now let's run this calculation. I'm just going to pw.x it first to see if it works. It does. Now let's submit it. Okay, after this job is done processing, we are going to do the same procedure we did and for this figure, and we're going to see how this potential out here is no longer going to be flat. You can see here, this is the z dimension of my unit cell. So this is like from 0 to 30, and 15 is the center of my unit cell, right where we had it. Okay, so the calculation is not done yet. Still going. Okay, oh, it's still going. Oh, job is done now. Okay, so now what we are going to do is just run the plotting file. Okay, now we are going to run the averaging file. Okay, now let us rename this. This is going to be average data. I'll just call it bare AU, and this will be average FAU. So now let's come back to our plotting script. And the original one, oh, let's actually just plot this one first, FAU. Okay, let's see how this changed now. So here was our original one. And you can see now that, well, definitely the electrostatic potential has changed. And this is why when you do these types of calculations, you need to do the dipole correction, because you can see here that the potential in the vacuum is now mimicking the potential that would be induced by an electric field. And this would give you, and if you don't correct for this, you're going to get erroneous results. And when you do computations, you want to be as quantitative as possible and as accurate as possible. And so in the next video, I'm going to show you how to apply the dipole correction that's going to largely sort of remedy this slanting feature in the potential in the vacuum. Okay, so a few things. This was a lot to take in this video. I usually don't like to move this fast, but I do want to keep the video short, and I want to give you as much information as possible since you can watch these videos again. Just a few things when doing the calculations in quantum espresso, you really want to use a very tight K-point mesh and be as accurate as possible in your electronic structure calculation. You also want to use optimized geometries of nuclei, so you wouldn't just use this structure here. You would have to optimize this, and there's probably going to be some repulsion between the gold and the fluorine. So these are not optimized nuclear coordinates. So with this video, what I hope to show you with this video was this feature here, that the electrostatic potential is now erroneous, so to speak, or mimicking the potential that would be in the presence of an electric field in the vacuum. So you can see these features here. And what we're going to do in the next video is we're going to apply a dipole correction that's going to basically cancel out this effect and make it flat here, well, flat-ish. We'll do that in the next video. Okay, take care. Watch this video more than once if you need to. If you have any questions, give me a shout out in the comments. Just let me know. Okay, bye.